Oh, but
Hello. This is a Baltimore Ravens consulting project by Sean Rappaport and Alistair King. The Baltimore Ravens have hired you as a consultant to help their team win games. The head coach, John Harbaugh, believes the team should not worry about how many offensive plays they run per game. The team has hired you to determine if Coach Harbaugh's ideas are correct.
so let's look at their past games. So we have 20 games that we can look at, and overall, like the points to plays run ratio is pretty consistent, besides one outlier that we'll get to later, which is this 72-48 point game.
So, first thing we did was create a line of regression. So we put our data into our calculator and did the lin reg thing, and we got y equals 1.506x minus 68.805 with a correlation coefficient, or R, as 0.939. And so we interpreted this in this particular way. So for the slope, for every additional offensive play the Ravens run in a game, the model predicts that they will score about 1.5 additional points. So that's what the slope means. The y-intercept is the model's predicted score if the team ran 0 plays, which would be negative 68.8 points. But because a team cannot score negative points or run 0 plays, this intercept doesn't actually have a practical on-field meaning. It kind of just sets the vertical position of the best fit line so that it fits the particular data points better.
Yeah, so next we calculated our residuals, which are the observed value minus the predicted value, which is y minus y hat. So we found that the residuals were pretty constant between -4 and like +3, with one outlier that I discussed earlier, which is that 72 plays run game where they scored 48 points, which gave us a residual of 8.4. So so uh Ari said that the linear model was a good selection for our data because apart from that one clear outlier, the residuals are tightly clustered between -4 and +3, and show like no systematic curvature as the number of plays increases, because the points bounce off randomly above and below zero with roughly constant vertical spread. The assumptions of linearity and constant variance are satisfied, so a linear model is an appropriate choice for these data.
So looking back at a graph of our original data, these are just the raw data points we see here, like what Sean just said about the prior slide. This linear trend is pretty clear. So next we did a linear regression t-test. So our claim was the team should not worry about how many offensive plays they run. And so how do we specifically interpret this? We interpret this as there's no linear relationship between plays and points, because if they weren't to worry, then they must not affect points. So our null hypothesis is that this p equals 0, and alternate is just not equal 0, with a level of significance alpha of 0.05.
So next we found our t-stat and our p-value and our critical value using the linear regression t-test calculator function. We found that our t-stat is 11.59. Our p-value, which was practically zero, it was 8 to the -10, so we just called that 0. And then our critical value, since it's a two-tailed t-test, was 2.101 and -2.101.
So we graphed this out, and we decided to reject the null hypothesis because our p-value, which was basically 0, is less than alpha. And also on this graph, we see that the t-stat falls within the rejection region.
So we were able to say, this is our interpretation, at the 5% significance level, there is sufficient evidence to reject the claim, and the number of plays, or the claim that the number of plays run per game does not impact the number of points scored. So based on our linear model, we would advise John Harbaugh and the Baltimore Ravens football team to run as many plays as possible to increase their points.
So John Harborough looked at the data, points out this one outlier that Sean's been mentioning a lot in this presentation, where they scored 48 points on 72 plays in one game. Based on this, John determines they should score 1.5 points per play for all of their games. Is his thinking correct or incorrect? Well, firstly, no, we think no, his thought process is not correct. Firstly, in a 72 play game where you score 48 points, the rate for that particular game, if you're only looking at that game, is 0.67 or like two-thirds, not 1.5. So even just looking at this game, we see that's not the case. If we look at the average points per play over all 20 data points, it's 2.67. So John Harborough is wrong. We think that this 1.5 number he got, which was the slope of our trend line, it comes from the linear regression trend line slope. And this slope tells us how much the expected point total increases for every additional play relative to the intercept, but this doesn't tell us the average points per play.
Yeah, so the Baltimore Ravens are currently in this example preparing to play the Steelers, and John Harbaugh knows that they need to score as many points as possible to win. John predicts that they will need to score 36 points to win, yet he does not know how many plays he will have to run. So we set this up as plugging in 36 into our linear regression and then plugging in that number for the regression line to give us an X of 69.59 points. But since you can't have half a play or 0.59 points or plays run, we rounded that up to the nearest whole number, giving us that the Ravens will have to run at least 70 plays in order to score 36 points against the Steelers.
Hi, Dr. Joe. Um, Next, Joe Flacco is going to miss the next game for the Baltimore Ravens. The coach knows that they will not be able to run as many plays because he's such a great player and so critical to the team. So, based on our model, what would be the prediction for points if they only managed 50 plays? So, again, plays is the X in the trend line. So, we just set X equal to 50 and we plug it into our linear regression. So, here we get 6.495. So the predicted points scored if there are only 50 plays, 6.5, similar to what Sean said, you got to round up. So, we'll say 7, or you could round down, say 6. But since 50 lies outside the range of the data, we didn't see anything with 50 in our data set. The range was 53 to 72. This is an extrapolation of the data based on our linear regression model.
Thank you, Dr. Joe.
Thank you, Dr. Joe.